żeby to podłonem, bo ci śmiści.
Well, as you know, today we're going to talk about lightnings. First of all, we have to think about that in the clouds there are happening many things due to the air, due to the little particles of water, due to the little particles of ice, and the movement among them. First of all, let's think that when movement occurs inside the clouds, due to the heat, the heat goes upwards. Let's imagine this as little waves. Little waves are flowing. Let's think about them as circles. Little circles, they go up and they are heat, so they tend to move. These little circles, these little heat particles collide with freezing particles, freezing water particles, and these freezing particles go down, and when they collide, it occurs friction among them, so it occurs an interchange of charge. The freezing particles become negatively charged, so they stay at the bottom part of the clouds, so negatively charged, and the heat particles become positively charged, so they go to the upper part. It's difficult to draw them, so let's going to draw a little few of them. So the upper part is positively charged, and the lower part is negatively charged due to the friction, due to the climate. This is the first important part. Then we have to think of an hypothetical scenery where we have the ground. We can draw a little house. No blue. We have a little house, and it has the ceiling, in this scenery we have also a tree, but it's brown. Sorry. It's brown, and it has the branches, green branches, right? So we have the scenery, and we have to think, to remember that same charges repel and different charges attract. So in the ground there are many particles that have electrons and protons among them. Well, also neutrons, but because they are neutral, they doesn't matter. But let's imagine that these electrons and protons are going to react to the storm. So it will happen that many of the small particles, of the negative particles, are going to go inner the earth, because they want to be far away from the negative charges. So they want a more distance among them. Let's think that they want more distance, and in the upper part of this scenery, let's talk about the surface of the earth, there are going to remain many positively charged particles. Like that. So this will happen, and this will also happen in the in where there's water. It is dangerous to be in the water when there's a storm, because water it's a better conductor of electricity. It's a better conductor than earth. So that's why it's dangerous. So let's think that because it's better conductor, if you are in there, electricity will have a better path to travel. But we'll talk about this in a minute. So when this happens, we have electrostatic charges all among the storm. So when the clouds have the negative particles down, we have what we call an electric field. So the electric field will go in this direction. All this, imagine that we have also clouds in here. I'll draw them in a minute. We have clouds also in here. So the electric field will go downward, and because of the electric field, all the air that it's in between the ground and the clouds will have a, let's call it, a different kind of charges. All the charges will convert into charges that will allow the electricity to pass. Scientifically speaking, all the air becomes like plasma due to the ionization of the electric field. So many people, when you are, let's draw a little man. If you are in a storm and you feel that your hair goes up, or that many specific clothes also go up, this is because of the electric charges. It's because of the electric field. So that means that the air is preparing, let's call it like that, to strike a lightning. So it's dangerous to be in there. So because of the electric field, this will allow this will prepare the scenery for the lightning to occur. When this happens, the electric field goes in this way, but all the positively charged particles try to go up. So they will go up through all the things in the ground, but specifically in the pointy parts of the things, in the branches of the trees, in the edges of the house. And if we talk that you are the pointy end in ground that there is nothing near, let's imagine that there's no house, there's no tree, you are the pointy end. So that's why it's dangerous to be there, because you also become positively charged. when this happens, the lightning, that it's not a lightning in that moment from the sky, and will go to the pointy end of something. In this case, the pointy end of the house. So it will go to that place. But it's not the lightning in that moment. It's just like the path that the lightning will follow, because due to the electric field, it won't reach the place that you're looking for. It will just be in a middle part, and the electric field will allow the positively charged particles to make the other path. Draw it like this. They will go up due to the electric field, and the lightning will go down due to the negatively charged particles. So when they collide, they finish the path that the lightning will follow. So all the electrons will go down, and they will strike. When this happens, you have a highly charged, you receive many electrons in that moment, and all the air around the lightning will hit in a millisecond and will go away. This movement, where the air goes away in a very fast moment, will make a sound that we hear as a thunder. Now, let's check this problem in order to understand what is happening in numbers. Well, first of all, we see that during a lightning strike, a cloud from the ground, the current is as high as 25,000 amperes and can occur and last for about 80 microseconds. So, how much charge is transferred from the cloud to the air during such a strike? Well, we have to think about the formula that it states that current it's equal to the charge over time. Okay, so if we use this formula and look for the charge, our new formula would be I times T. But we have to convert the numbers that are given in order to international measures. In this case, 40 microseconds, we convert it to seconds. So if it is 40 microseconds, it is 40 times 10 to the minus 6 seconds times 25,000 amperes. If we plug it into a calculator, we obtain that the charge it's 1 coulomb. But we have to check to check the part B of the problem. Does the lightning carry a huge or a small charge? Well, first we have to think the difference, all the values that are involved inside a problem. There tends to be a confusion between energy and power. In a minute we will explain it, because the difference among between power and energy is that power is the ability to convert energy in a period of time. So we can think about it like this, with the formula that P is equal to E over T. If we look at this, it means that power is the amount of energy during a period of time. Also, there tends to be a confusion of what is charge, current, and also voltage. So let's write all the formulas involved. As we saw, I is equal to Q over T. Also, we know that power is equal I times V. And if we make a simple analysis, well, we know E is equal to P times T, power times time, but this is also equal to I times V times T. Why? Because power in this equation says that power is energy times voltage. And finally, we get the first equation. In the case of a lightning bolt, V and I are both really high, so the power is extreme, but T, the time as we see, is really low, so the high current and short time mitigate each other in a form so that there is not an immense charge. So if we continue analyzing with some data, we know, well, only to remember that in a lightning bolt there are transferred up a media of 10 to the 20 electrons in a moment, and it is transferred approximately 10 kiloamperes and several hundred million volts. So that's why it is the voltage is high, the charge is high, no, the current is high, but the charge tends to be not very high because of the moment.
Just a young gun with a quick fuse. I was uptight, wanna let loose. I was dreaming of bigger things and wanna leave my old life behind. Not a yes sir, not a follower. Fit the box, fit the mold, have a seat in the foyer. Take a number. I was lightning before the thunder.